Ionization of water. We were talking in the previous video terms like ionization and dissociation, and let's define what those terms are. They kind of go hand in hand. Dissociation is the process by which acids or bases separate in water. Ionization is the formation of the ions as a result of dissociation. So they happen pretty much simultaneously. What does this pertain to when it comes to water? In the previous videos for chapter 14, we were qualitatively describing acids and bases. In this video, we're going to get into quantitative explanation for acids and bases. How do we quantify something is an acid or a base or neither, or if it's a strong acid or a strong base. But before we do that, we need to have an understanding of what happens with, or what can happen with water. Water can act as an acid or base. It's something that we call amphoteric, meaning that it can have both of these natures. If we take two molecules of water, what happens is that H2O, water is H2O, oxygen is bonded to two hydrogens. The oxygen in the center, which is the central atom, has two lone pairs on it, making it a little bit more negative than your hydrogens, which have no lone pairs on it. So what happens is that the hydrogen from the other water molecule is attracted to the lone electrons on the oxygen. These are negative, these are electrons. This is a hydrogen, which is more positive. Opposites attract, likes repel. So the hydrogen attracts to the negative oxygen, ripping it off of the other water molecule. In doing that, we have the hydronium ion form as a result of that. So I have the green here showing what happens. And this has more of an acid characteristic. Remember, we defined acids as proton donors containing hydrogen ions. Okay. Then what happens to the other, the second water molecule? What happens to the other oxygen and the other hydrogen? They stand alone with an overall negative charge and form the hydroxide ion, which is how we defined what a base is with the Arrhenius definition of a base. Well, what does this mean? We're going to use the concentrations in the solution, the concentration of the hydronium ion or the concentration of the hydroxide ion. The concentration of those ions in solution help us to quantify if something's an acid or a base. You may have heard of it as the pH. Okay, what is pH? pH is the amount of hydrogen in a solution, the power of hydrogen. And it's based upon the concentration of the hydronium ion that is in that solution. So now what we want to do is we want to talk about this term pH, some descriptions, and then we're going to look at how to calculate it. But how we can tell if a solution is an acid or a base and how strong of an acid or a base it is depends upon the pH, which is the amount of this ion that is in solution. The pH scale is how we can quantitatively determine if a solution is an acid, base, or neither, therefore being neutral. And we can also use the pH scale to determine how strong or weak that acid or base is. You may wonder, where does the term pH come from? pH comes from the idea of the power of hydrogen. The classic definition of an acid, the Arrhenius definition, is that it contains hydrogen ions. Okay? The pH scale is actually a logarithmic scale, so base 10. Okay, increases in increments or decreases in increments of times 10. The pH scale corresponds to the molar concentration of the hydronium ion. Now, hydrogen ion does not stay as plain old hydrogen ion in an aqueous solution. It will bond to a water molecule, as we just saw in the previous board, and form the hydronium ion. So you are determining with the pH what is the molar concentration of the hydronium ion. So we are going to use logarithms, our calculators, to do it. And that is how we're going to determine the pH of a solution. So how do we calculate pH? To calculate the pH, we take the negative logarithm of the hydronium ion concentration. Sometimes you will see it written as the negative log of the hydrogen ion concentration, meaning it's the same amount. But remember, hydrogen does not stay intact as hydrogen. It bonds to a water molecule and forms the hydronium ion. But sometimes you see certain books showing it this way, and sometimes you see it written that way. Your textbook has it with this designation here. Okay. So to calculate the pH of something, we need to know what the hydronium ion concentration is. Okay, when the hydronium ion concentration is greater than 1 times 10 to the negative 7th, that results in a pH below 7, which classifies an acid. When the hydronium ion concentration is below 1 times 10 to the negative 7th molar, then the pH is greater than 7, and we have a solution that's a base. When we have the hydronium ion concentration equivalent to the hydroxide ion concentration, and that being 1 times 10 to the negative 7th molar, we have a pH of 7, meaning we have a neutral solution. We want to keep in mind that solutions that are strong acids have very low pH values, and strong bases have high pH values. Now, how high and how low do we go? The pH scale goes from 0 to 14. With 7 being neutral. We're going to do calculations in a moment, but I want to alert you to a chart in your book, figure 14.4. And you have charts like this on the internet as well, but I want to show you in your book. Figure 14.4 gives you the pH values of common substances. If we look at the top of the page, substances that have very low pHs, hydrochloric acid is one of them. It's a very strong acid. We keep looking, following that, gastric juices, which would be hydrochloric acid. Okay, that's very low. Lemon juice, okay. Coca-Cola, you saw me test that in the demo in the previous video, and I also tested oranges mixed with water in the previous video. Okay, so the soda about 3, the orange about 3.5. They both fall under 7 in the acid range. Remember, we said that a lot of your foods are acids. So if we look at the pHs of those foods, we can see that they are definitely below 7. So you can look at figure 14.4 here, and you see lemon juice, vinegar, carbonated beverage, oranges, apple juice, tomato, okay, all in the range of 4 and below. And then you have coffee, you have potatoes, you have milk, okay, they're in the 5 to 6 range, okay. So you have all of these food products that are in the acid range for pH values. Okay. And then you get to, on the pH scale, so we're working our way from 0 up to close to 7, and you have the pH of 7, okay, you have pure water, okay, it's right at 7. So when I did the litmus paper test in the previous video, you saw that I did test water, and it did not change either blue or red litmus paper to any color because it's neutral. Continuing to look at this chart here, okay, drinking water is a little bit above 7. And that was a question in one of the lab, pre or post lab questions. And it said, drinking water, is it acidic or basic? And most people answered it with the correct answer, that it's slightly basic because you're adding some chlorine in there, residual chlorine, to have the water disinfected. So when it passes through all the piping systems in the city and into the home, that you still have some residual chlorine to keep out bacteria. So that chlorine makes it slightly basic, slightly above 7, but not too much. Blood plasma is about 7.4. Okay, so still in that, it's slightly basic, but still in that neutral range. Let's kick it up to a pH of 8. Now we're definitely above 7. We're pH values of 8 and above. A lot of your cleaning products, detergents, bleach. It's a picture of the ammonia Windex with ammonia. I tested that in the previous video. Okay, they turned the litmus paper to blue. Right, and then you have liquid Drano, which has has sodium hydroxide, a very high pH, about 14. Okay, that's used to react with all of the grime that is in the piping of the sink, but the sodium hydroxide will not react with the metal. It will not corrode the piping. It'll just corrode everything else that's attached to it. Okay, so refer to this chart again, look at it, okay? I know that me holding it up to the camera isn't so clear, so make sure that you take a look at that for yourself so that you can get a better look at that. And you may find other charts on the internet as well that look very similar to that. So we said that we have acids below 7, bases above 7. Strong acids have very low pHs, and there are only 6 strong acids. And the 6 strong acids are hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, and perchloric. So the only 6 that are strong acids. All of the other acids are considered weak. These are the only 6 that are considered strong. High pH, strong bases: sodium hydroxide, lithium hydroxide, potassium hydroxide, barium hydroxide, strontium hydroxide, and calcium hydroxide are strong bases. All of your other bases are not considered to be strong bases. Things like bleach, which is sodium hypochlorite, contains the hypochlorite ion. Ammonia forms the ammonium ion. Even though they're very reactive, they are not considered strong bases. Because remember, strong acids and strong bases, the amount of ionization, they completely ionize. Okay, it's not a matter of reactivity, because you have strong acids and strong bases that are very reactive, and you have weak acids and weak bases that are also very reactive. But we're talking about the amount of 100% ionization. So when we calculate the pH of a solution, we need to know the hydronium ion concentration. If it's a strong acid, then it's equal to the molar concentration. What is the pH of 0.11 molar hydrochloric acid solution? Well, we need to take the negative log of that hydronium ion concentration. Now, everybody has a different calculator. So I'm going to walk you through the example with the calculator I have, which I know a lot of you have as well. And if you have a graphing calculator, it'll work the same way. Some of you I know will have a different scientific calculator, and you will have to enter in the calculation backwards than from what I show. And if any of you have any issues with your calculator and getting the answer that I'm getting here, you can look at the card that your calculator came with, or you can ask me for help to how to enter in logarithms. I'm going to show you with the calculator I have. If you have this calculator or a graphing calculator, you enter it in exactly as it's written. Negative log 0.11. Make sure you use the negative button, not the minus button. This is your negative button. It's right below the number 3, right below the number 3. You would do negative. Then the logarithm function, log, not natural log, this is the base 10 log, not ln. That's natural log with the Euler number base. You don't want that one. You want this one, log. Press that, negative log, and then you see it opens up a parenthesis for you. I know there's a glare. Let me stand here to see if it helps with the glare. Okay. We would enter in 0.11. Close the parenthesis. Enter. Okay. So we have in our display readout 0.9286. I hope I'm reading it right backwards. Okay. So pH would be 0.96. No units for pH. No units. Now, if you're wondering about significant figures, okay? Significant figures for logarithms, I don't want you to be concerned about it, but I will just briefly tell you how it works with the logarithms. You look over here at what is in the mantissa here, and you have 2 total non-zero digits, so 2 significant figures here. So your final answer should have 2 significant figures for the decimal. So total number of sig figs, total number of decimals. Don't be concerned about that, okay? I don't want you to go crazy with the significant figures for logarithms. I want you to be able to calculate pH values, okay? So when you're looking at this video, make sure you're using your calculator to see that you get the same answer that I got, okay? Those of you that have a calculator that's not like mine and that it's not a graphing calculator, you'd have to enter in the concentration first, then the logarithm, then the negative. That's usually how it works with the calculators that are not like mine or that are not graphing calculators, okay? So if any of you encounter difficulty, you can consult the card that your calculator came with or ask me, okay? But if it's not working as I showed it, it's because your calculator has a reverse entry way that you have to do it, okay? Let's do another example of calculating a pH value. But it's very easy. Once you know how to use your calculator, it's very easy to do, okay? Let's do another calculation. Okay, let's do 2 more examples with calculating pH. Let's calculate the pH of a Drano solution, okay? Liquid Drano, liquid plumber, I was just talking about it, that has a hydronium ion concentration of 2.6 times 10 to the negative 13 molar. Is it an acid, base, or neutral? Okay, we want to calculate the pH. pH equals the negative log of the hydronium ion concentration. 2.6 times 10 to the negative 13. Okay, yes, we have exponents for concentration values. We need to be able to enter them into our calculator to get the answer. So pH is the negative log, open parenthesis. Now I need to enter in the concentration. All right, I'm trying to do it backwards. 2.6. Now, however you like to enter in exponents, that's your preference. I like to use the EE key, second EE. to the negative 13th power, negative 13. And now I need to close the parenthesis, and then I do enter. And I have 12.58, then a non-terminating decimal. So the pH would be 12.59 if I keep the significant figures. And that would be the pH of the solution. Okay? So negative log 2.6 times 10 to the negative 13th, close the parenthesis, enter, and you get this, okay? You get a non-terminating decimal. You say, well, what if I rounded it to 13? What if I had it at 12.6? I would accept any of those answers, okay? I just followed the significant figure rules for logarithms, a total of 2 significant figures, a total of 2 significant figure decimal places. That's the rule for significant figures in logarithms. I don't want you to get too crazy with that, though. Okay, is this an acid base or is it neutral? It's a base. I knew that all of you were saying that as you're watching it. It's a base. And I know you all knew that, so I can hear you through the camera. Okay. Let's do another calculation. Let's calculate the pH of a blood plasma sample, given that the hydronium ion concentration is 3.6 times 10 to the 8th molar. So again, pH equals the negative log of the hydronium ion concentration, which is 3.6 times 10 to the negative 8th. So we put that into our calculator. Okay, negative log, negative log. Okay, now I need to put in what the concentration is. So the concentration is 3.6 times 10. I'm going to use the EE function to the negative 8th. Close parenthesis. Equals. Enter. 7.44 non-terminating decimal. All right, pretty close to what the pH is for blood plasma. Your textbook on figure 14.4 has it at 7.4, very close, okay? So pH calculations are very straightforward. Take the negative log of the hydronium ion concentration. The rest of chapter 14, they talk about some reactions of acids and bases and acid-base titrations, and so they actually pertain to lab. Reactions of acids and bases, you actually saw some of them in lab with experiment. Well, actually, you may not have seen them because we may have been out of the class then. But you may have, from the videos that I had sent, metals react with acids. So the magnesium metal reacting with the hydrochloric acid gave you hydrogen as a result. Reacting a carbonate with an acid. If you have vinegar in your house and you have Tums, mix them together. You'll see a reaction, okay? You'll have an acid, the acetic acid and vinegar and the Tums, the calcium carbonate, and they will react together. So section 14.7 talks about reactions of acids and bases. Section 14.8 talks about titrations, and titration lab, the online lab for that was last week, and you watched the videos on that. You saw when you react an acid and a base together in a neutralization reaction, you get water and an ionic salt for your products. Okay, the ionic salt varies depending upon what the acid and base are, but you always have water that forms. So a neutralization reaction, you have an acid and a base, and what a titration is used for, titration is if you do not know the concentration of a solution, you can react it with a reactant that you know the concentration of, and then by determining the amounts that reacted, the volumes, and the known concentration, you can calculate the moles, and then you can calculate the concentration, the molar concentration. So sections 14.7 and 14.8 are good to read. So I'm going to write that up here to make sure that you read those sections, just to give you some more background information on topics that were addressed in lab, whether in-person lab or online lab. It gives a little bit of information. And 14.8 talks about acid-base titrations. There are other types of titrations that are done. A titration is done to determine a concentration, but a lot of times in chemistry, especially introductory chemistry and general chemistry, we focus on the acid-base titration. So just read those to conclude chapter 14.